Hello and welcome to QED Lecture 5 Part 6. Now, the previous section of the lecture dealt with concepts and language that you can apply to just about any hypothesis test. So now we look at some particular types of hypothesis test, starting with the t-test and then looking at these other kinds here. So the way they differ is that different kinds of tests have got different types of hypotheses, often depending on the types of variables, the types of data you have. They often need, well, they always need assumptions, so that the type of assumptions you need for each test is different. And then the thing that affects you most when you're doing the test is the mechanics, the formulas if you're doing it by hand, or the commands you have to use with Stata or Excel, and how you get these probabilities alpha and beta. And the previous slide just showed you what alpha and beta are. Alpha is the probability of the reject results if the null hypothesis is true. That's what's often similar to the p-value. And beta is the thing that you often don't get with many statistics tests, which is a big weakness of statistics testing in general, is that you often don't know beta. Anyway, a number of tests get these probabilities using the t-distribution, and imaginatively we call those t-tests. So let's have a look at some of those. First, let's recap the one we've already done. The one sample t-test, where you have a test value for the population mean, and essentially somebody's claiming this, or from previous records you have this mean value for whatever the harvest used to be, or the number of trees people used to have, or whatever the thing was, and you want to know whether that is now, or for the population you're interested in, is this the mean now? And you need a single random sample to test that. So the null hypothesis is always this, population mean is just mu, but then the alternative can be two or one-sided depending on what you're trying to show. If you're just trying to show that this is inaccurate, or you're testing whether it's inaccurate, then the alternative would be that it's just not mu. So you would reject this if you get something much bigger in your rat sample, or if your sample is much smaller. That would be a two-sided alternative. Population mean is not that. Or you could be trying to show that there's been an increase, in which case you're only going to reject the null if you get a much bigger value. So that would be alternative like this. Or you could be looking at for a decrease. So you're looking only for an alternative like this. So these two are one-sided. So you must be clear about whether you're doing one-sided or two-sided before you carry out the test, at least in principle, if not in practice, depending on how ethical you are, which is very, I hope. So, for example, small farmers in South Africa, current variety of maize yield gives you this on average. Bring in some new seeds. You hope it's going to increase things, of course. 3 years later, you take a random sample of farms. You want to know, has the mean now increased? Here's the null and alternative. So the null is that it still is that 5, 1, 12. The alternative will be one-sided because we are looking for an increase. So we go for the one-sided alternative. Then we grab some data. Here's data on 24 farms. If you just eyeball it, you can see that there's quite a lot have done better than 5, 1, 12, but there are a few that have done worse. So we're looking for the mean of this, so that's 560. So the question is, does this give us evidence that the mean in the whole population has gone up? Conceptually, what you're doing here is you're saying that, okay, this is your random sample of 24, but there are millions and millions of possible ways that you could collect a random sample of 24 farms. And out of those millions and millions of ways, what percentage of those samples would have a mean that's this much bigger than 512 if, in fact, the whole population still really had a mean of 512? What's the chance that, if that's still the case, you could randomly select one sample of 24 and get a mean this big? That's why you use this t formula. To use the t formula, you need to know how far above the mean that is compared to the mean of all the possible samples, and then work out how far that is in terms of how many standard deviations. So this is a standard deviation of the mean, as you pick lots of means of size 24, and that's given by the population mean divided by the square root of n. The population standard deviation divided by the square root of n. We don't know population standard deviation, so we use the sample standard deviation. So that's based on these numbers here. This number is estimating the population standard deviation. And this is for individual farms, but when you pick 24 farms at a time, that's going to reduce the amount of variation in the numbers. So you divide the standard deviation by the square root of n. So that's this number divided by square root of 24 is this. So that gives you the standard deviation of the mean of samples of 24 when you pick 24 at a time. So now we can do the t calculation, which is this is the distance above the mean divided by this to give you how many standard deviations. So this is about 3840 divided by that gives you 2.7184. So you are approximately 2.71 standard deviations above the mean. And what percentage of t-values are that big? Well, you can look it up in Excel. So type this in, put that number in there. 23 is the number of degrees of freedom for that t-value, and it tells you that only 0.00628 of t-values are that big. So a very small proportion. So this is your p-value. That's the probability of getting a sample with a mean that big. So what you do is you'd report that p-value. So if the null hypothesis is true, if the mean yield is still 5 on 12, the chance of picking a random sample of 24 with a mean as big as this is 0.006128. So this is where you need to think about it. So pause the video if you need a bit more time. What would you go for there? Okay, hopefully you've paused it. So because it's a less than 1% chance, you should have been saying that you reject H0 with 99% confidence. So you should be going with A. So because it's below this, you can reject H0 with 99% confidence in favour of H1. So if you're writing this up in a report, dissertation, coursework, you'd give this as the p-value and then say, oh look, it's below 5%, it's also below 1%. So because it's below 1%, you just report this standard thing that you can reject at the 99% confidence level. You could say at the 1% significance level, which means the same thing. So just note in QED, in assessments and so on, you should know how to do that calculation by hand for a small sample, though you wouldn't have to do it for coursework. But we expect you'd know how to do it for a small sample, and we expect you could do that Excel thing. But for all the other hypothesis tests, including the other kind of t-tests, we're not going to expect you to know how to calculate results. It takes far too long. But what you need to be able to do is you need to be able to know what kind of test you need in a certain situation. You need to know how you're going to carry it out using Stata, and then when the results come out, you need to know, well, what are those results telling. So if we were doing this using Stata, which would be sensible, just put the data into Stata. I've called it maze yield, call it whatever you want. This is the command, t-test, maze yield is equals 512, and it gives you the answers. And so the main challenge is get the data in there, put the right command in without misspelling it and getting a lot of red error messages, and then look at these three things here. You've got to decide which one to choose. So because our alternative was a one-sided one that's greater than, we're looking for this one here. And as you can see, the probability is exactly the same as calculated previously, rounded off. So Stata gives us the same p-value. So to conclude from this, those are the null alternatives. Maze yield still 5 on 12. Alternative is now bigger than 5 on 12. 5 on 2, sorry. We found a p-value of under 0.01. So we can reject H0 at the 1% significance level in favour of H1. And then please make sure that when you interpret things, as well as you must give this technical conclusion, but also for the non-statistical audience, maybe the policymakers or other readers, explain what it means. So this means that the evidence strongly suggests that mean maze yields have risen in the area since the new variety was introduced. So it could be just coincidence, could be, but it could be that that maze is now actually improving people's livelihoods and so on. But certainly you can be pretty confident that that random sample represents what's really happening in the rest of the population, although you can't be sensible about causality. Okay, in the next video we're going to move on to 2 independent samples t-tests, which is still a t-test but a slightly different sort. But I'll leave that to the next video, and thanks for watching.